Hello and welcome to part 1 of lecture 21. Here we're going to begin chapter 26 from Survey 11th edition. And in this chapter, we are finally officially moving to modern physics. Everything that we've done in the textbook in our 2 semesters of physics before today would have been considered more of classic physics. Okay, those lines are a bit blurred. Give you some perspective. We've talked about thermodynamics. That would, last semester that is, and that falls under the 17th and 18th century, not necessarily classic because it has its own approaches and pedigree, but certainly before the 20th century. Most recently when we were talking about optics, that's a field of study that really came into its own in the 1800s, the 19th century. But now with relativity, and then moving into nuclear physics and quantum physics, quantum mechanics, all of that is in the 20th century. Kind of the earliest 20th century, what we teach here in introductory physics, but definitely considered modern physics. Okay? All right, so let's begin with modern physics. The first topic's relativity. This is associated with Einstein. It's one of his big theories. Okay? We're going to be talking 99% about something called special relativity. That'll make a little bit more sense in just a few moments. Okay, so here we are with the beginning of this chapter. The title here is Invariance of Physical Laws and the Relativity of Simultaneity. Okay, so what's going on there? Why, what does that mean? Why don't I just call this Einstein's special relativity? Well, because these are kind of the topics that we're going to be building on, I'd say, more directly. Einstein's theory is just kind of a building block that's going to get us there. It's kind of just a key word, and so on. Okay. All right, what are our objectives? Our objectives are to learn the 2 postulates of Einstein's theory of special relativity. So that's definitely part of what we need to do to understand the idea of invariance of physical laws. And then we want to understand why different observers can disagree about whether 2 events are simultaneous, but will never disagree whether either event occurred. Okay? So that's a lot to take in, right? And it's tricky. It's hard to reconcile. You won't want to convince yourself it's right. I'm going to try to do as good a job to convince yourself it's right. You have to get there yourself. You have to understand why this makes sense while not making sense, okay? Because it can't. It's a process, okay? All right. So what's going on here? So we'll start with the classics, right? We'll harken back to classical mechanics, classical physics to remind us about the term relativity, okay? Because that term doesn't mean Einstein's relativity. It's something else, isn't it? Okay. So what is Galilean relativity, which would also just be ordinary garden variety relativity, everything we've talked about at this point. Okay. Well, it's simply this. It is a law that states that the velocity of objects appear different depending on the velocity of the observer. Different depending on the velocity of the observer. In fact, one consequence of Galilean relativity is you can say all velocities are relative. Okay, I'm at rest relative to my desk, okay, where I'm giving this lecture right now, but I'm not at rest relative to the moon, right? So all velocities are relative. And there's a bit to unpack there too with that word appear, right? Do I really mean appear? Well, no, it's a measurement. It has a real effect. So we won't worry too much about that word. That idea of something appearing to be different and truly being different will become very important, but here I'm not going to worry about it. Okay, so all velocities are relative. Okay, now this took the form of a relative velocity equation. We've seen it before. So it would have been this: VA with respect to B as a vector equals V with respect to C plus the velocity of c with respect to b. The idea there is that I always say that we're sandwiching in the c, and then so it doesn't show up in the final result. Okay? Well, that's an equation we've used. Okay? Should look familiar, something you can remind yourself about. Now, there's going to be a new way of writing it, because I want us to get used to some notation that we're going to be using for Einstein's relativity, measurement of velocities and so on. And it's a good time to introduce it now. Okay? So there's an equal way we can write this equation. I won't worry about it being a vector because we're going to do everything 1D here. And what that equation would look like would be, it would be V equals V prime plus U. Okay? So let's see about why that is. Well, because each of these, VAB became V, they each correspond. VAC became V prime, and then VCB became U. What does that mean? Well, let me just label them in the new equation. So V is the velocity, and it would be the velocity measured by an observer at rest. Okay? So this will be velocity measured by observer at rest. Okay? V prime would be the velocity in a moving reference frame. So velocity in moving reference frame. Okay, don't worry about that term if it doesn't sound familiar. Reference frame, get back to it. And then U is just the velocity of the reference frame, okay? And that would be relative to rest. Okay, so quick check, does this make sense? Well, if we look and we've got the velocity measured by an observer at rest, well, if the velocity in the reference frame is 10 meters per second, but then the reference frame is also moving at 10 meters per second, then the observer is going to say that, oh, well, it's 20, right? It's kind of like if a train went by and was moving to the right, and someone in the train threw a ball to the right, I would observe the ball as the sum of those two velocities, the velocity in the train plus the velocity of the train itself, right? So it would appear to be moving faster, okay? So that's the idea. Makes sense, right? Why are we writing it differently? Well, because here when we were writing it, in addition to being vectors and allowing for 2D, it was all about one thing relative to another. So it was always A relative to B relative to A. So we didn't really focus too much on the idea of a reference frame, right? We didn't really push the idea that the train was the reference frame. It was just another object, another one of our three things, our A, B, or C. A often was the ground, so it could have been rest, right? But we just want to be a little bit more specific with this version. We really want it to always be around a reference frame. And that often is a spaceship or, this kind of thought experiment idea that, we have the spaceship that can move really, really fast, like 99% the speed of light, right? We don't really, but it's something we can conceptualize. And there are things that move that fast that we do make measurements about. Particles that decay at known rates, then they do move at appreciable fractions the speed of light. And these particle processes, we measure them, we observe them, and so on. Just we don't do it in spaceships with lasers and so on. So that's it. We're just going to be talking a lot about reference frames using this kind of notation like this. In particular, the type of notation I really want you to be familiar with is U. Okay, because U is the letter I'm always going to use for the velocity of the reference frame. U. Okay, the velocity. All right. Okay, so that's Galilean relativity. A little bit of introduction to notation we'll come back to. But let's get to what you've been waiting for. Let's get to actually looking at the Einstein's theories. Why are there two postulates? Are these his two theories? In fact, there's more than two theories associated by Einstein, but I said the two most famous, special relativity and general relativity. But no, that's not what the two postulates are. The two postulates together mostly form what is known as special relativity. So Einstein's theory of special relativity has two postulates. Okay, so let's talk about that. And that's really what I want you to know. Okay, so the first postulate says that the laws of physics are the same in any inertial reference frame. Okay. So that's it. Okay, so the postulate states that the laws of physics are the same in any inertial reference frame. Simple as that, okay? Do you remember what an inertial reference frame is? You know, that's a term. I like to bring it up a lot, but you'd be forgiven for forgetting or not knowing, okay? It's a technical term. It just refers to any reference frame that's not accelerating, okay? So anything that's moving at constant velocity is considered an inertial reference frame. That's always an approximation, okay? So I'm going to say that me sitting at my desk in my office is an inertial reference frame, okay? I'm at rest, essentially. But you might be like, oh, well, hold on, you know, the Earth is moving at a constant speed, but it's not moving at a constant velocity because it's taking a circular path. Therefore, there's a centripetal acceleration. Yes, there is, okay? And that centripetal acceleration is incredibly small, okay? Whether we're talking about the centripetal acceleration relative to the sun or the centripetal acceleration relative to the center of Earth, because you got two separate rotations there, they're both tiny. Most importantly, I'd say for measurements, they're both tiny relative to the acceleration of gravity. Okay, so that's a big one. So they're not going to really show up in observations. That's why we can have expectations about objects. Okay, they'll, like Newton's second law or first law for that matter, will apply. Objects will remain in motion unless acted on by an external force. Okay, that would apply to my office pretty well, except those external forces like drag and friction. Okay, but anyway, the point is that's an inertial reference frame. Anything that's not accelerating, but important thing, that does include not turning. Okay, so it has to be something moving at constant speed in a straight line. Okay. So that's constant velocity. So inertial means constant velocity, not just constant speed. Constant. Okay. So what does that mean? Okay. So that means it is not possible to throw a ball and observe its motion in a way that tells you your velocity relative to another frame of reference. Okay? It is also not possible to use a coil and a magnet to generate a current in a way that tells you your relative velocity. Now, I'm not saying there's anything special about balls, coils, or magnets here, but the point is that you cannot perform any experiment in order to determine your velocity relative to another frame of reference. Nothing will tell you, okay? I can't tell, right? Because again, back to my office. I can't tell if I'm at rest or if I'm moving at 1,000,000 miles an hour because I'm not accelerating, right? We kind of know this. I mean, think about like when you're like in a plane that isn't being jostled around by turbulence. That plane's moving very quickly, but you walk down the aisle, right? You don't feel like you're not walking down an aisle that's at rest, do you, right? That's a perfect example, right? You can't tell. There's no, and not only can you not tell kind of on a personal level, there's no experiment that you could perform, okay? You might be like, oh, just look out the window of the plane and measure the fact that you're moving above the ground and just do a simple calculation about how far you went, okay? But that's not allowed here. That's not an experiment that actually is taking place in your reference frame. That requires observing another reference frame. Okay? So you have to have a self-contained experiment. There's no experiment you can perform entirely within that reference frame that would tell you how fast your reference frame is moving to another. It's pretty amazing, isn't it? Okay? Let me write down just the general statement. Okay? So there is no experiment, okay, and I'll say mechanical, electromagnetic, or otherwise, that can be performed entirely in one reference frame that will, what's the word I want to hear? I'll just tell you, reveal, like allow you to calculate, but that will tell the relative velocity of that reference frame. The rel-vel of that ref frame. Okay? Simply impossible. And this is such a cool thing. You just imagine just sitting down and thinking about this, being like, wait, okay, there's no way to tell, because all these laws are supposed to be invariant. Okay, are they really invariant? Okay, yeah, I guess if they really are, then there's no way to tell. Huh? Okay, and it kind of makes sense. But then, what comes from that, right? What is the consequence of that? Well, it's the second postulate. Okay, because here's the thing. I didn't just kind of by random, happenstance choose the example of, mechanical example because it's kind of accessible, like the ball, and there's no way you can bounce something, no way you can let a pendulum swing that's going to tell you your velocity, right? There's no way. Now, and again, quick reality check if you're kind of being skeptical here. Certainly there are experiments you can perform with pendulums that will tell you your acceleration. I know I've mentioned in class, some of you have heard of the idea of a Foucault's pendulum. It's like the one they have at the Academy of Sciences in San Francisco. It spins in a circle, and that tells you the rate of Earth's rotation. So you can tell that you're in a rotating reference frame because the pendulum doesn't always swing on the same axis. So yeah, there's experiments you can do. Absolutely. Sure, you can tell when you're accelerating the car because things will fly forward or fly backwards, right? You can measure that, So certainly you can do an experiment to find out you're accelerating, but you can't for velocity, okay? But in addition to the kind of everyday mechanical ideas, the reason I mentioned performing an experiment with a magnet and a coil or some circuit is because of the second postulate, which I'm getting to in just a second, don't worry. But why, right? Why did I have to mention that idea, something that was electromagnetic? Well, because maybe you can imagine doing some experiment, if circuits would work differently, or if I had a some sort of electromagnetic induction sort of effect, I'm moving a magnet in and out of a coil generating a current. Well, maybe if I did that, point in one direction or point in another direction, maybe that's a thing. Yeah, sure, maybe mechanics all work the same because gravity works the same, but maybe electromagnetic fields are susceptible to velocity. Maybe they're the way to tell it. Maybe that's it. And that could have been the way the universe works, but that's not the way the universe works. Because, first of all, it simply doesn't work. You can't show any difference between, velocity measurements with magnets and coils or any sort of electromagnetic effect. And second of all, then that would have a whole cascade of other consequences. Okay. Then again, what I'm about to say has a cascade of consequences. Okay. So let's get to it. So because of that, because the physics is non-varying, we have this idea that, so we have this idea then that the speed of light must be the same in every reference frame. Okay, where did that come from? Well, it just came from the idea that you can't perform an experiment, right? Because if the speed of light did depend on how fast you were going, then all those effects, all those things like the permittivity of free space and the permeability of free space, all these calculations we make for Gauss's law and Ampere's law, then all of that would depend on how fast you're going, because all of that depends on light and the speed of light. Okay? So if physics is really invariant, if you can't perform an experiment to determine your velocity, then the speed of light must be the same in every single reference frame. It must be like a fundamental, just like the strength of gravity is fundamental. Okay, that's it. That's the second postulate. In all inertial reference frames. You might be like, really? The speed of light can be different in non-inertial reference frames? No, I'm not saying that. I just want to make sure we're sticking to the special theory of relativity here. Okay. So it's saying that the speed of light is always the same because Otherwise, you could devise the experiment that would determine your velocity, okay? Otherwise, physics would not be invariant in reference frames, which is just invariant in reference frames. It's just the laws of physics are the same, right? All right. And you could devise an experiment to determine your velocity, or to tell your velocity. Tell your relative velocity, okay? And that would be the relative velocity of your reference frame. But I'm shorthanding here. Okay, that's it. That's all there is. Got to be all the same physics. Thus, the speed of light's got to be really a constant. Okay, wow, right? So anyway, what is that, right? Well, that just says that the ultimate speed limit must be, the speed of light, because if it is a constant, then you can't go faster than it, okay? And I won't spend so much time justifying this. I know I've been very wordy here. So I'm simply going to say that a consequence of the second postulate is that nothing can travel faster than the speed of light, right? And again, that might be a little unsatisfying, but I think I've hopefully been more robust with these explanations leading up to this. So a consequence of the second postulate, which itself follows the first postulate. In a technical jargon, we call the speed limit, the ultimate speed limit of the universe, we call that a corollary of the second postulate. Okay, so a consequence of the second postulate is that nothing can travel faster than the speed of light. Okay. All right. So that's it. We're laying the groundwork here. Okay. We've got Einstein's postulates, kind of harkening to things you've heard before. We've got this idea. There's this ultimate speed limit of the universe. It's the speed of light. Okay. What is its value? Well, you can kind of take a look at that. Like the speed of light has a value of 3 times 10 to the 8 meters per second. It's exactly 3. It is exactly 3.00. It's like 2.999 something. Okay. So that's our speed of light, and also the speed limit of the universe. Okay. So now, moving away from that a little bit, I want to get into a couple of kind of definitions, and I'm going to go ahead and include the illustration of them in the second video. On this one, I'll just focus on the terms. So let's just get these out of the way. Okay, so an event. You might be like, okay, this is kind of a big step. How do we go from Einstein's postulates to defining an event? Well, this has a specific meaning within special relativity. So we'll say in special relativity, okay, an event refers to an occurrence that happens in all reference frames. Okay, so in special relativity, an event is an event. Okay, well, we'll just say is an occurrence, to look for in a synonym, it's kind of a synonym, that happens in all reference frames. Okay, right? But that's not a satisfying definition. Why? What do I mean here? In other words, okay, so we'll say i.e. an event is irrefutable. Okay, an event is irrefutable. Okay, it cannot be argued with. An event happens. Everyone agrees that events happen. Okay, so for example, 2 light waves reaching a sensor that only triggers when the 2 waves reach the sensor simultaneously is an event. Okay? That's very specific, I know. Okay, but we'll come back to that in video 2. Okay, or another thing, the explosion of a star is an event. It either blows up or it doesn't. Okay, so those are examples of events. Let me put a couple of those down real fast. Okay. So let's do the quick examples because good to have them in writing. So a star supernova is an event. No one would disagree that it happens. Either it does or it doesn't. Okay. A sensor being triggered by two waves reaching it simultaneously. Okay? That would also be an event. It either happens or it doesn't. No one can disagree about that. Why am I making a big deal about this? Because that's crucial for relativity. We have to have our feet firmly placed in reality if we're going to understand something as strange as the fact that time and space can change depending on how fast you're going. Okay? So, again, star blows up or it doesn't. The sensor is either triggered or it's not. Okay? There's no alternative universes here. There's not, one case where it does happen, another where it doesn't happen. It either does or doesn't for everyone in the universe. Everyone would agree. Okay. All right. So, this leads us to relativity of simultaneity. This is the first place we're going to start. Okay? So, since an event is absolute, right? Irrefutable. And the speed of light is invariable, same in every inertial reference frame. Okay? There is an amazing and unsettling conclusion that two events are simultaneous for one observer, but are not for another. So what if there's two supernovas? Each of them is an event, okay? But there's no such thing as a double event, right? There's not like, both of them together are collectively event. No, they're separate events. So in one reference frame, those two supernovas may happen at the same time. Okay? They're simultaneous. They both blow up at the exact same time. Maybe one to the left and one to the right. In another reference frame, they're not simultaneous. One of the explosions happened before the other one. It didn't appear to happen before the other one. It actually did. Okay? Why? Why just come up with some nonsense like that? Because it's not. And it's absolutely a consequence of the first two postulates, which makes sense, right? Laws of physics must apply everywhere. Therefore, there's, that means that speed of light must be an absolute because the laws of physics are built on that speed of light. Okay, so that's it. That's it. We have to give something up. Okay, let me write it down. So since an event is absolute, again, just think irrefutable, and the speed of light is invariable. There is an amazing and unsettling conclusion/consequence that two events are simultaneous in one reference frame, but are not in another. All right, well, that's it. Okay, that's the first really strange thing we've said. Okay, and everyone thinks of relativity as being this very, very strange theory, right? Well, here it is. Okay? So, again, it is a consequence of the stuff we said before. Okay. Okay, so was there something else I wanted to say on that? All right, so we're almost to the end of this video. The last thing I wanted to mention was this Michelson-Morley experiment. Okay, and what the Michelson-Morley experiment concluded was that light does not require a medium to propagate it. Okay, so kind of we'll think about this as kind of another piece of the puzzle to make sure we are understanding where we're going to go from this. So this was an experiment that proved using optics. Okay, I'll say here that proved that light does not require a medium through which to propagate. You might be like, so what? I never really thought it did. Well, but then again, if you thought about waves, then the question must be baked, because sound requires a fluid to propagate through. There's no sound in space, for example. You can't have a chain reaction of molecules bumping into one another to propagate sound if there's no molecules to bump into one another, okay? So then what about light? You know, how does light move, right? Well, up until the Michelson-Morley experiment, because the consequences of there not being a medium for light were jarring, okay, which we're getting to, well, people thought there must be this thing called the ether, okay? And the ether was thought to permeate the universe, and it was maybe composed of very tiny particles that were yet to be discovered. You know, people speculated it, and light must use it to propagate, okay? Well, if there's ether, then when we move through space, we must be moving relative to that ether, and by we, I mean our planet. And so the experiment was based on the velocity of Earth through space, and then it would have measured a change in the light depending on shooting a light beam parallel to Earth's velocity or perpendicular to Earth's velocity, but it didn't. So it disproved the existence of the ether. And if there wasn't this ether made out of ordinary particles or something, then there must not be any medium for light, okay? So that proved that light really moves through a vacuum. And that means that if there's no medium for light, that means that there's no absolute reference frame. Because the ether, in addition to being the medium for light, was supposed to be kind of like it's like the grid of space. Because everything was moving through the ether, and the ether was just sitting there. But it turns out it's not there. So then there actually is nothing that we are in reference to. And that's really where you're going to see special relativity comes in. Because it says if there is no fundamental, if there's no universal reference frame, then that kind of means that time and space is a bit squishier than we thought it was. It turns out that time and space isn't just like this firm thing that the planets and the stars are sitting in. Instead, it is part of the same thing that makes the planets and the stars. Mass and energy, time and space are all part of the same thing, okay? All right, well, we'll get into a good example of simultaneity in the second video,